Okay, we're back to do another 10 problems. So this is the WebAssign review for exam number 2. We've got, we're being asked to take just the derivative of this function. And notice we've got a product rule here, but here is just a constant multiple. So the first part, its derivative is just, I guess maybe I should mark it down here. Its derivative is just going to be 4e to the x. That's its derivative. And I've got this minus. I'm going to put that, and I'm going to put a big parentheses here. And now I'm going to take the derivative of the inside part. And when I take the, well, not the inside part, sorry. I sort of think of it, I'm going to put this parentheses here. I take the derivative of this product. So it's the derivative of the first part. So that's going to give me 2x times the second part unchanged, e to the x, and I didn't take its derivative, plus the first part, x squared unchanged, times the derivative of the second part, which is also e to the x. Remember, e to the x is this function that is its own derivative. So which one is derivative? Well, again, this e to the x is a derivative of e to the x. This e to the x is the original e to the x, but you can't really tell. Anyway, let's do a little bit of algebra. So we've taken care of the calculus. We get 4e to the x minus 2x e to the x. And I got to distribute this, so I distribute it to this part. I also need to distribute there, so I get another minus x squared e to the x. Now, this is a correct answer, but again, you see an e to the x. We could factor all of those out, and it might be, it might not be. But if you don't see this as one of your answers, again, you should be able to put it in and it would count it. But anyway, we could factor out an e to the x, and then we're left with 4 minus 2x minus x squared. So be able to see that part. It might have a final answer like this. Again, not the one above is a correct answer. Yep, is correct. But we just have to use our algebra skills to get it into different forms. Okay, number 12, derivative of this function. And again, we've got e to the x. So this one, we're going to use the chain rule. So we take the derivative of the inside part, which is the derivative of the exponent. Derivative of 5x plus 7, its derivative is just going to be 5. Derivative of 5x, 5. Derivative of 7 is 0. So its derivative of the inside is just 5. Then we multiply by the derivative of the outside function, which is e to this 5x plus 7. Again, e is its own derivative, and so that's its derivative. Again, if you want to think of it, we do get a natural log of e, but this here equals 1. When we multiply by 1, it doesn't show up. So our final answer will simply be, sorry, I'm going to get back over here. I got two screens going. Will simply be 5e to the 5x plus 7. And that's our function's derivative. That's it. And again, this one going to be very similar, except we've got a really long function in here, so the inside derivative is going to be a little bit more complicated. Since I'm going to slow it down just a bit, I'm going to rewrite that exponent so that as I get its, because this 7 over x, I want to rewrite that as 7x to the minus 1. So that's the inside function. When I take its derivative, I'm going to get 4x minus 5, taking the derivative, right? And then I get a negative 1 coming down, so I get negative 7x to the minus 2. That's the derivative of the exponent. That is the inside function, times the derivative of the outside function. E to some exponent, its derivative is always going to be e to that exactly same exponent. You can write it in this form. And again, we get a natural log of this, natural log of e, but that's just 1. So this is our answer. And not really much we could do. You might see this x. So here we have number 14, and looks like we're going to have a chain rule with a product rule. So we've got two things being multiplied. So we've got this first part here and this part here. So these are two things being multiplied. We'll need the chain rule on the exponential function. First function, we won't be using the chain rule because it's to the first power. So let's break this up into a times b, and then, so we've got a times b, and then remember we'll use this formula that when we have two functions multiplied together, the product rule says take the derivative of the first one times the second one unchanged, plus the first one unchanged times the second one's derivative. Okay, so the first one is just x squared plus 1, and that derivative of that first one is going to be 2x. That's it, because derivative of 1 is 0. For the b part, we have 5x squared minus 1. So when we take its derivative, the derivative of the b part, we're going to take the derivative of the inside part, which is the exponent. So that's going to give us, and again, it happens down here on the line, 2x, and then derivative of 1 is 0, so just 2x. And that gets multiplied by the derivative of an exponential, which again is itself 5x squared minus 1 times this correcting factor of natural log of 5. And again, if it was to the power of e, we'd have natural log of e, which is 1, but we don't, so we've got natural log of 5, which is some number. You could plug this in your calculator, figure it out, but we're just going to leave it as natural log of 5. And again, you could put a parentheses here to get that part. So now let's put everything together. First, the derivative of the a is 2x. So that goes in first, times the b unchanged. So that's 5x squared minus 1 plus, so this is the first part here, a unchanged. So we get our x squared plus 1. And we're going to multiply now times the derivative of b, which is 2x. We'll put the natural log of 5 here. Just change it a little bit. And then 5 times 5x squared minus 1. Now that's a correct answer, but what you'll see here, and I think I ran into this with someone maybe on the homework problems or something, what you see is that 2x times 5 here, we've got 2x, skip over this part, 5 to the x squared minus 1. So what they may do for this answer is they may factor that part out. And then what's left behind? Well, if we factor this out, a factor of 1 is left behind. There's this invisible times, everything's times 1, right? So there's a 1 left from factoring it out. And then what's left here? Well, we've got this part and we've got the natural log of 5. X squared plus 1 times the natural log of 5. And again, you could distribute this out and maybe rewrite it, but I think this is about how in the problem they left it. And maybe we were, anyway, there was, we were comparing and we were wondering where that 1 came from. Maybe we did it in class. I don't quite remember, but this, there's these. Now, again, the one above it is correct and it should get counted as correct, but you can also factor out. So there's 14 for us. Let's go ahead and keep moving forward on these. 15, and just kind of get this pace and this rhythm. And you can you can watch these. So now we're into the part that's doing implicit differentiation. Let's see, what color do we have? We've got green. We'll go with green. So remember, I'll dispense with the dx because whenever I take the derivative of x, remember, I really get a dx, which is 1. We'll leave that alone. But when I take a derivative of y, the way I'm going to write it is dy dx. Okay, so every time I take a derivative of y, I'll write dy dx. Every time I take the derivative of x, there'll be an implied 1 there, and 1 times anything is just itself. So we look at this first part, and we see a product rule. We see a x times y to the 4th. Let me go like this. I think it might be easier if I bring it all over here. So when I take this derivative, I'm actually going to get 2 terms, right? Because a product rule gives me a plus. So the derivative of the first part, derivative of x is 1 times the second part unchanged, y to the 4th. That's it. When I go for the second part of the derivative, I take the derivative of the y. Well, let me go ahead. I'll write the first part unchanged, so I write down the x. Now I take the derivative of the y part. So the 4 comes down in front. This is going to be 4y to the 3rd. And since I'm taking the derivative of y, I get a dy dx. And this is not a 4. This is supposed to be a y. Yeah, see, it's a minus y. Okay, so that's the derivative of the first term. The derivative of the second term is going to be minus, well, what's the derivative of y? It's 1 dy dx. And that's all equal to the derivative of x is just 1. Okay, so now what do we do next? Let's we're going to factor out this dy dx because there's 2 of them. We need to factor them out, see what's left over. And while we're doing that, we can go ahead and subtract y to the 4th because this does not have a dy dx. So we want to get it to the other side. Do all of that in one step. So what we're left with is, okay, this is going to cancel out here. We're going to have x 4y to the 3rd. So we'll write that as 4x y to the 3rd. Just reorganize it. The dy dx we're going to factor to the back side. So I'm taking this and factoring it to the back. We come to this term. What is there? There's a minus 1. Take the dy dx and it's factored back here. So both of the dy dx's are now here. It's one of them. And then we have it equal to 1 minus y to the 4th. And the last thing to do is to divide by 4x to the 3rd minus 1. Those become 1. And over here, 4x y to the 3rd minus 1. And this is going to be what our answer will look like. That's what goes right there. Okay. Don't really see much that would happen. This is a difference of squares. You could factor it. I don't think it's going to do you any good. And again, it would be, I would just leave it. Okay, so let's keep rolling along. 16, implicit differentiation. Same type of deal. We're going to get a product rule with the first one. So we've got x squared y minus y squared equals 6. Okay, so this first part, product rule, let's go ahead and switch over to green. So the derivative of the first factor, x squared, is going to be 2x to the first power. The y tags along, nothing happened to it, and then there's a dx, right? The second part of the product rule is we're now going to take the derivative of the y. So we write the first part unchanged, x squared. Derivative of y is 1 times 1, and we get a dy dx because we took the derivative of y with respect to x. So that takes care of this first term. Remember, product rule gives us 2 pieces. Then we get minus, take the derivative of y, so the 2 comes down. y to the first, dy dx. That's really the only thing that got added with when we're doing this implicit differentiation. We just need to keep track of which rate we're talking about. And then derivative of 6, that's a constant. Derivative of 6 is 0. So again, what we do is we want to solve for the dy dx. So these things we're going to need to factor to the back. All right, we'll factor these out. While we're at it, this first term doesn't have a dy dx, so we subtract it over. And so that canceled out. We end up with x squared times 1, which is just x squared. And the dy dx is going to go to the back side. Could go to the front side, however you want to do it, that's okay. And then the next term, we've got minus 2y, so we get a minus 2y, the dy dx factored out. So that's all that's left there. 0 minus 2xy, so that's all that's left there. And then we just divide. X squared minus 2y. Sorry, so that'll cancel out. That's a 1. And what we end up with is dy dx, right, equals minus 2xy over x squared minus 2y. And I think that's about all you're going to see. Not really much to simplify there. So derivative, implicit derivative, just keep using our same derivative rules. We're taking derivatives of two different variables, x and y. And we'll see this again when we get to the related rates. And when we actually get a third variable involved, we'll have x and y, and everything's changing with respect to time. Okay, implicit differentiation with exponentials. Same kind of thing. I'm going to set this up because I'm looking here. We have two product rules. So there's a product rule on the first one. There's a product rule on the second one. So let's go ahead and move that over here. So as we talk about it, it's nice and it's more clear what we're doing. Okay, so this first part, we've got a multiplication here. We take the derivative of the first factor. Derivative of x is 1 times the second one unchanged. And again, we took the derivative of x with respect to x, so that's a 1 as well. Then we get a plus the second part. Remember, product rule gives us two pieces. Second part, we keep the first factor unchanged times the derivative of the second one, e to the y, its derivative, e to the y, it's its own derivative. But we were taking the derivative of something with y, so this gives us a dy dx, a marker I call it. And that's the derivative of the first part. So then I'm going to put this minus. I'm going to put a parentheses because what I'm going to do is I want to just, I don't want to bother with this negative, how it applies. So I'm going to leave it here on the outside. And then within the parentheses, I'll take the derivative and then I'll distribute it. Okay, so we've got two parts. I want to take the derivative of y. Derivative of y is 1. The second part is e to the x. It hasn't been changed. And when we took the derivative of y, we took a dy dx as our marker. Okay. Then the second part is a plus. The second term, we're going to take the derivative of the second part. So we've got y. E to the x is its own derivative. We took the derivative of x with respect to x. So that's a 1. We don't need to do anything there. Okay. And then that all equals 0 because the derivative of 1 is 0. That's a constant. Okay. And so then I just highlight what are the terms I'm going to have left. Well, anything with the dy dx. So these all be left. I'm going to now go ahead and distribute this because sometimes I have problems with this myself. I'll see people, they'll put it only on this first one. They'll leave this either as a plus or it gets confusing what happens. But both of these are going to be minus. Okay. So I need to get these parts. So I guess let me just rewrite it out. So we've got e to the y, because that's 1 times it, plus x e to the y dy dx minus, right? And actually I distribute it, so it's not a minus. Don't come back and redistribute it. That little, so that I'm going to just have minus e to the x dy dx. And then what's left here, we've got a minus y e to the x, all equal to 0. Okay, so I subtract anything that doesn't have a dy dx, and at the same step, I'm going to factor out the dy dx. Factor these guys out to the back, move these guys to the other side, and what ends up happening is the sign changes. So this first one's positive, it over on the other side it'll be negative. This one's negative on the other side, it'll be positive. And I'll just go ahead and show that, because we're subtracting e to the y and we're adding y e to the x, again, to both sides. And then as we do that, we are going to rewrite this as x e to the y. The dy dx is going to factor to the back side. So that's that part. This canceled. This canceled. Those are zeros. And then I've got a minus e to the x. And again, the dy dx, here it is. It's in the back. So 2 dy dx's become 1 dy dx's. That's the power of factoring. It's really here, if we wanted to redistribute, that's how we get the 2. And then over on this side, we see what we've got. Now, we might want to flop this a little bit. We might want to write it as y e to the x minus e to the y. And then what do? We just divide both sides by what's left over here. X e to the y minus e to the x. So this will now become a 1. And dy dx becomes equal to this over x e to the y minus e to the x. Interesting. So this is should be our final answer here. So keep rolling along. I'm not checking these, so but you go ahead and check them. You try yours, you check them. And we've got a couple days at the start of the week where we can follow back up. But just follow along. It's the process that's important to pick this up. Okay, so we're starting, looks like, into, and I think we worked this, maybe we worked this one in class, I think. Yeah, I think worked 18 and 19 in class. So, but we'll go ahead and keep going with this. So the main thing I look here before I read too much is compounded continuously. So we need the formula that the accumulated value with continuous interest is the principal e to the RT. PERT is how I remember it after all these years. How fast is the balance growing after 4 years? So it's going to ask us, what we really need to know is the derivative of this balance. So 20,000 is invested. That's the principal. So we have this accumulated value function is going to be 20,000. E is a constant. It's a natural number. It comes from continuous compounding. The R is 3.5%. So we write that as 0.035 t. T is our variable. So we're going to take this derivative. What we want is the derivative of A. And that's going to be 20,000 is a constant multiplier. So it comes along for the ride. When we take the derivative of the exponent, 0.035t, our derivative is simply 0.035. Now that comes down onto the main line. you might put it in front or back. It's just everything's being multiplied. And then the derivative is the exponential itself as well. So that was the chain rule. The derivative of the exponent comes out front. And then it's not like when we had powers that this is coming down, but we took the derivative up there, if that makes any sense. So this is our derivative. And what we want to do is we want to find the derivative at 4. So it's really in respect to t. So we just plug all this in. And let me find my calculator here. Let's see. Wabbit. It should be down in the W's. Oh, I know it's on the desktop. But I should have okay. Come over here. There we go. So let's just come back here. We'll clear it out. 20,000 times 0.035 times e second natural log to the 0.035 times 4, all up in the exponent. We hit enter. 805. .19 to the nearest cent. Okay, that's that one. Yeah, we did work one in class as well, and we did this one as well, but again, we're going to go ahead and do it. It might be slightly different anyway. This is in review. So with this one, we have to take the implicit derivative to get dy dx. So derivative of x squared is 2x. That's that first part. Second part, we've got a product rule, x times y. So the first derivative, and I'm gonna just kind of carry this negative with the 10. I'm gonna say it's minus 10 because that's going to come along. Derivative of x is 1, so I have minus 10y left. And if I wanted a dx, I could put that, but so whenever I take the derivative of x, I don't have to have the marker. And then I would have plus, but I notice I've got this negative 10, so plus times negative 10 is going to give you another negative 10. Now I'm going to take the derivative of the y part, so I get minus 10x. The x goes along for the ride. Derivative of y is 1 dy dx. So implicit derivatives, we just, every time we take the derivative of y, we get this marker, and then everything else is the same. And then it's all equal to 500. Derivative of 500 is 0. This one's a little more simple. There's all the dy dx is already, there's a single one, so we don't have to factor it out, but we get everything that's not a d, that doesn't have dy dx, and we move it to the other side. So we'll subtract 2x. We'll add 10y, and we'll do that to both sides. And so that is going to give us 0, 0. It gives us minus 10x dy dx equals, and again, I'm going to switch the order. I'm going to write this as 10y minus 2x, and then we divide both sides by negative 10x. And what you could see is you could factor out a 2 out of everything in the top. If you factor out a 2 and factor out a 2 in the bottom, this reduces. Again, you don't have to, but so take the 2 out, and what do you have? You've got 5y minus x. And in the bottom, if you factor out a 2, you got 2 times, actually maybe factor out a negative 2. Then you're left with a 5x here. So you cancel. This is a negative 1. So you redistribute it here. You're going to get a plus x and a minus 5y. Yeah, because it's negative. What we end up doing is we put it up here. It just makes it all a little nicer. So our final answer we could write as x minus 5y. So notice how this negative that I factored off of the bottom has come to the top. We can move it up there, and it changed the order there all over 5x. So that's the derivative. It's also the slope of the tangent line at that point. But to get that equation of the tangent line, what we need to do is actually figure out what the point is. And so what we're given is that x is 10. But notice if we just plug in 10, we need to know what y is. To figure that out, we have to plug in the x up here. Okay, so we're going to plug in 10 for each of these x's. So we get 10 squared minus 10 times y. So that's that part here, all equals 500. So it looks like we get 100 minus 100y equals 500. I think the one we did in class, it had 700 if I remember correctly. Subtract 100 from both sides. I'm running out of room, but so we end up with negative 100y equals, subtracting 100 will give us 400, right? 500 minus 100 is 400. And then divide by negative 100. So we get that y, in this case, is going to be negative 4. So when x is 10, y is negative 4. So, somewhere we're going to write that down. We're really going through the point 10, negative 4. And now we can use that to get the equation of the tangent line. The first thing we want to do is get the slope of the tangent line. So the slope is going to be using the derivative, with 10 plugged in for x, negative 4 plugged in for y. So we get 10 minus 5 times negative 4 over 5 times 10. That gives us 10 plus 20, so it looks like a 30. 5 times 10, that's 50. So we get 30 over 50, which reduces down to 3/5. So that's our slope. And now we just use linear equation stuff. Y equals mx plus b. Y equals 3/5 x plus some y-intercept. And we can find that by plugging in the y, negative 4 for y, and the x, 10 for x. So again, we get negative 4 equals 3/5 times 10 plus b. 5 goes into 10 twice. 2 times 3 is 6. Subtract 6, right? Because it's 6. We're going to subtract it from both sides. Negative 4 minus 6, that gives us negative 10. I know I did a lot right in there, but that's our y-intercept. So our equation, y equals 3/5 x minus 10. And again, I did one that had slightly different numbers in the class for Friday. That was 1016, something like that. Let me do one more, and then I'll take a little break, maybe a longer break, and get these posted so that you can start working on them or start viewing them. And then, but you should keep working through these today and Sunday. And then I'll finish up the other 20, and those are going to be probably more, those are going to be our problem-solving ones, then we'll do that. Okay, so find the exact location of all the relative and absolute extrema. So one thing I'm going to have you watch out for is this word exact. It might have a relative. I think we're okay here, but sometimes if we have like an e to the x, they actually want your answer in terms of something like e to the 5 or something. Okay, whatever that would be. But we don't want to round anything, so we need to use fractions and all that kind of stuff. Absolute extremum function. Again, what I want to do is, it looks like there's going to be 4 points, right? I want to graph this, and I want to look at it. They're giving me a domain. X is going from -2 to 2. So, I can set my graphing window. That helps. All I got to do is figure out, well, how high do I need to go? If you plug in 0 for x, you'll see that the y-intercept will be 12. So probably the y value needs to be at least 12. So let's go ahead and take a look at what this graph would look like. Okay, so we'll turn this on. We'll go to y equals, and we will put this function in. If I can see it, I got to move this over. So we're going to put in 8x to the 3rd, arrow down, minus 24x plus 12. Then I'm going to go to my window, and it's already from -2 to 2, so that's good. The x is. Why I'm going from 0 to 40, I don't know that I need to. How about -20 to 20? I don't know this for a certainty, but I'm just trying to give myself enough room so I can see what's going on. And I'll graph it. And if we need to come back, we'll come back. We could also look at the table, but we'll just do this. So I can see it goes up, and I missed it. I need to go higher. I don't have to go too far down here. I've got my minimums are going to be down here. So let me go up higher just so I can see everything. Maybe 40 would have been good to leave it at. And this could probably be -10. And that'll just help us. Yeah, 40 was plenty. -10 is good. So I can see a relative, possibly absolute maximum here. I can see a relative, possible absolute minimum here. And then I remember I've got to check my 2 endpoints. And then when I list them, I'm supposed to list them from order your answers from smallest to largest x. So what we need to do is we need to start at the endpoint here. I need to find what is this value, because it's at least a relative. It might be a absolute maximum. So what I want to do is I want to go to the table. And I'm going to look up -2. Okay, I've got this. I could reset the table, but I'm just going to scroll until I get to -2 and then -4. So I know I've got that. -2, -4, and that's some kind of a minimum. It might be an absolute, but it's certainly at least a relative. I've got to find the other minimum, which will be here, because as I come back, I can see this is going to be a maximum, and then I get a minimum here. So let me go to the next one. I can find this maximum by going second calc, maximum. Notice I haven't used any algebra. I could have taken the derivative, set the derivative equal to 0, and that would find me the 2x values where I'm going to get those in between the maximum and the minimum. However, since I've got the graph up, I can just use my graphing tools. That's my preferred way to do it. Okay. We'd also want to know that, I could take the derivative and find it. When I set the derivative equal to 0, I would find the critical point, or at least the critical x value, then I'd have to plug that into the function to get the critical y value. This one, I get everything all in one swoop. -1, 28. And again, I know that's some kind of a maximum, and I'm just going to have to wait to compare it to the endpoint to see what kind of a maximum. So we come here and we've got -1. We'll round that 28. Okay, and I'm just going to label that as some kind of a max, and I'll come back whether it's relative or absolute. I can now go to the next point. I see it looks like it's going to be a +1. We're probably right. So if you would have taken the derivative, set it equal to 0, you would have got x equals -1 and +1. You would have then had to stick those into the equation, to the function, to figure out the y values. This method of doing the graph just allows you to find these things without the calculus, but it gives us a visual. It's a modern way of doing math. We've got these tools, let's use them. And we see so much, we really see what's going on a lot better. So we need to round this, we'll round it to x equals 1, y is -4. So we've got 1, 4. And we've got a minimum. And what I can notice is the minimums, oh wait, -4, sorry. Yeah, it's -4. See, I can see what's going on too. So we can see these minimums, they are both absolute minimums. The absolute minimum value is -4. It occurs at 2 places. So we'll label these as absolute minimums at this point. And I have a feeling that this is going to be, that's going to be like 28. Let's see if I'm right or not. So we can come here. We could also go, let me just show you one. So I could scroll to 2 and just look it up. From the graph itself, remember the other thing I could do is I could go to calc and I can use value. Now I plug in what x value? 2. I want the endpoint at 2. So I put 2. And since it's going to 2, it'll find it. It does give us that when x is 2, y is 28. 2, 28. Okay, so there's another way, and I see the equation, I see where it's at. Notice all this good information I get from here, and I see that this is a maximum, this is that they're both absolute maximums. Again, there's only one absolute value, maximum value of 28, but it occurs at 2 places. So that's number 20. I'm going to post these videos, and you keep working on things. We'll have some more videos coming shortly. Thanks.